Hello everyone. Today's session will be on physical properties and chemical reactions of aldehydes and ketones. I know there are many chemical reactions associated with aldehydes and ketones. Let us discuss one by one each of the chemical aspects, each of the reactivity aspects. We should not forget one simple thing, that the linkage is C double bonded O, for which the carbon, which is the carbonyl carbon, behaves as an electrophilic center because it has a delta positive character, and the oxygen which is bonded to the carbon is behaving as a nucleophilic center. So the main reactions that are associated with carbonyls is nucleophilic addition reaction on account of the presence of the delta positive character in the carbonyl carbon and on account of the presence of the multiple bond between carbon and oxygen. So let us start our discussion. Everyone, starting with the topic physical properties of aldehydes and ketones. Whenever we discuss about aldehydes and ketones, the first thing that we do is we talk about boiling point. Okay, so we compare the boiling point and then next we talk about solubility. These are the two most important points to discuss. Okay, so let us start with boiling point. Boiling point actually depends on type of interaction between the particles of the compound that we are talking about. So here one information we can see, methanol is a gas at room temperature, ethanol is a volatile liquid, other aldehydes and ketones are liquid or solid at room temperature. That means when the molecular mass is increasing. Now boiling point of aldehydes and ketones, they are quite high. And they are high on account of the interaction that is present between them, and the type of interaction is dipole-dipole interaction. From the data that is given here and from our previous video, the discussion of in the previous video, we can say that the boiling point order goes like this. Alcohols have highest boiling point on account of the presence of intermolecular hydrogen bonding between them. Then is aldehydes. Why aldehydes? Because aldehydes are having strong dipole-dipole interaction. Then is ketones, RCOR I can write, then is ketones because the dipole moment or the dipole-dipole interaction or the polar nature of ketones is less than that of aldehyde. Then comes ethers, ROR, that is the ether linkage because ethers are less polar than ketones, they are less polar than aldehydes. And then comes hydrocarbons of comparable molar masses. So what are the types of interactions that develops in ROH? It is intermolecular hydrogen bonding that actually forms associated molecules in alcohols, for which the boiling point of alcohols are high. Next comes aldehyde. Lower aldehyde will be more polar, of course, then higher aldehyde. After aldehyde comes ketones and they have dipole-dipole interaction. Of course, this interaction, this polarity of the molecule decreases from aldehyde to ketone to ethers. And in case of hydrocarbon, there exists van der Waals interaction, weak van der Waals interaction. They are weak interactions. Next, coming to the text part. Solubility. Lower members are more soluble. They are soluble almost in all proportions in water. Why? Why is it so? Because of the formation of intermolecular hydrogen bonding. Because of the formation of intermolecular hydrogen bonding with water molecules. So this is what we can see, that it is an example of a ketone. Similarly, we can see an example of an aldehyde forming intermolecular hydrogen bonding with water. So lower members like formaldehyde will be more soluble than RCHO, and the solubility order also is HCHO is more soluble than RCHO is more soluble than RCOR, which is a ketone. And the reason behind the solubility for all the cases is capability or ability of forming intermolecular hydrogen bonding with the water molecules. So this is what we have discussed. Solubility of aldehydes and ketones decreases rapidly on increasing the length of the alkyl chain, because that is the hydrophobic part, and when the size of the hydrophobic part increases, the solubility in the polar water molecule decreases and the intermolecular hydrogen bonding becomes weak. This bonding that is being shown, this is the intermolecular hydrogen bonding. This is your intermolecular hydrogen bonding in the book. Next is the aldehydes and ketones. They are fairly soluble in organic solvents like benzene, ether, methanol, chloroform, etc. Remember that organic solvents can dissolve all organic compounds. So the solubility in organic solvent is quite fair. Okay, so moving on to the next example, 8.2, I think it is. So it is arrange the following compounds in increasing order of boiling point. When you are arranging it in increasing order of boiling point, you have to arrange it from lower boiling point to a higher. And see the one which we have discussed. This is hydrocarbon, this is ether, this is aldehyde, and this is alcohol. Had there been a ketone, then what would have been the position? Can you predict? If yes, then tell me in the comment section that in example 8.2, if the example is say of a CH3, CH2, C double bonded O, CH3, that is a ketone, where would it be located in the order of boiling point? Less than this, higher than this? In that manner, give me the answer in the comment section. And this ketone has a name. It has 1, 2, 3, 4. So it is methylprobute. It is butanone. So it is butanone. Remember that it cannot be the linkage. The ketone linkage cannot be in the terminal position. So if I say butanone, it is obviously 2-butanone. Next, moving to in-text question. Arrange the following compounds in increasing order of their boiling point. So this is your aldehyde. So I number it as 1, which is aldehyde. This is alcohol. I number it as 2. And this is 3, which is ether. And this is 4, which is hydrocarbon. So again, for in-text question 8.3, I want your answer in the comment section. What is the increasing order of the boiling point? Okay, lowest for which one, then for which one, and then the last two also, which is having highest and which is having lower. So I'll be waiting for the answer in the comment section. Do not see the solution from any of the app, from any of the GPTs, from any of your answer books, refreshers. Please try out on your own. If it is wrong also, not to worry. I will give you the correct reason. I will find out where your concept goes wrong. Okay, moving on to the chemical reactions. In the introduction part, I have said that carbonyl compounds are susceptible to nucleophilic addition reaction due to the polar nature of the bond. This oxygen has a delta negative character and the carbon has a delta positive character. So if there is a nucleophile in the reaction, this nucleophile will obviously attack. Where will it attack? It will attack in the carbon and the oxygen opens up. That means the pi bond opens up towards oxygen. So this is the carbon atom, which is sp2 hybridized carbon. This is sp2 hybridized, and so the structure is a trigonal planar structure. This is the trigonal planar structure, and this is your sp2 hybridized carbon, for which it is having a trigonal planar nature. And now the nucleophile is attacking the electrophilic center delta positive, and oxygen opening up as O minus. And this step is your slow RDS step, because that involves nucleophilic attack. Always remember that this center, the carbonyl center, should be less hindered. Then only the reactivity will be more. And the electrophilicity of this carbonyl carbon, the delta positive character, should be more. So this is the electronic reason that it should be more. More is the delta positive character over the carbonyl carbon, greater is the tendency of the nucleophile to attack the carbonyl carbon. So I can say that HCHO formaldehyde has maximum rate of this nucleophilic attack than RCHO. Why is it so? Because in case of RCHO, the R group has plus I effect, which reduces the electrophilicity or the delta positive character over the carbon. It also causes greater steric hindrance in comparison to formaldehyde. Then comes your ARCHO, benzaldehyde. Steric factor, electronic factor, both are there. And then comes RCOR, that is ketone. This is the order of rate of the reaction towards nucleophilic addition in carbonyl compounds, aliphatic, aromatic, as well as ketones. So mechanism of nucleophilic addition reaction, the first step is the slow RDS. The second step is a fast step which involves protonation. See, the intermediate captures a proton, and this is your intermediate, and the carbon over here is sp3 hybridized, for which the structure is a tetrahedral structure. After proton abstraction, that means this O minus abstracts the proton and forms OH. So it requires catalytic amount of acid in the medium, which makes the reaction faster. So it abstracts H and becomes OH, and this is your addition product. Nucleophilic addition product. What type of addition product? It is nucleophilic addition product. So rate of the reaction depends on, that is what reactivity is talking about. Rate of the reaction depends on steric factor and electronic factor. So steric hindrance is minimum in aldehydes, or I will say lesser in aldehydes than ketones. So aldehydes are more reactive than ketones. This is the rate of the reaction towards nucleophilic addition. Now, if I talk about aliphatic aldehydes, then aliphatic aldehydes are more reactive than aromatic aldehydes. So again, in aliphatic, I will say HCHO is more reactive than RCHO, is more reactive than ARCHO, than ketones. This is the order which we have discussed just few minutes back. So, and why is it so? Because as we move from HCHO in comparison to RCHO, to ARCHO, that is benzaldehyde, and to ketones, the steric factor increases, crowdedness increases, and it hinders the nucleophilic attack over the delta positive carbon. And electronic reason means when the size of A and B increases, then it actually has plus I effect, for which it reduces the delta positive character or the electrophilic nature of the carbonyl carbon. This is an important question, example 8.3. Would you expect benzaldehyde to be more reactive or less reactive in nucleophilic addition reaction than propanol? It is plain and simple comparison of aromatic aldehyde. Benzaldehyde is aromatic aldehyde and propanol is aliphatic aldehyde. So this discussion we have already done. Let us see it once more. First thing, it is sterically crowded. So greater steric hindrance. So number one thing is steric hindrance. Steric hindrance is greater. Number two is electronic factors. Okay, so in electronic factors, what it is, because of minus R effect, the electron density is moving out of the ring. See, it is coming towards a carbonyl. Why it is coming towards a carbonyl carbon? Because this is delta positive and this is delta negative. So delta positive carbon will take electron from the benzene ring. So it takes the electron and O minus opens up like this. So electron density is moving out. And since it is moving out towards a delta positive carbon, so it reduces the polarity over C double bonded O and it reduces the electrophilicity. So I can say minus R effect reduces the electrophilicity over carbonyl carbon. If I say electrophilicity, it actually means delta positive character over carbonyl carbon. I think it's quite clear why it is benzaldehyde having less reactivity than any other aliphatic aldehydes for nucleophilic addition reaction. Now, some of the examples of nucleophilic addition reaction. Number one is addition of HCN in the formation of cyanohydrin. This reaction is slow reaction with pure HCN and is favored and catalyzed by a base. Now this is your base which can abstract the acidic proton of that is H. The base abstracts acidic proton and generates the nucleophile which is Cn minus. So the role of the base is to increase the rate of reaction by proton abstraction, and you can add on by saying and generation of a better nucleophile that is Cn minus. That gives a complete answer or complete reason why a base facilitates the reaction. After that, you can see the nucleophile is causing nucleophilic addition reaction, how it is attacking the carbonyl center and the pi bond opens up and generates O minus. So you can see O minus over here. And in the last step, O minus abstracts proton. Since you have a cyano and a hydroxyl group over here, the name is cyanohydrin. That is Cn and OH attached to the same carbon. That's why it is known as cyanohydrin. Okay. Next, addition of sodium hydrogen sulfite. What is sodium hydrogen sulfite? It is NaHSO3, sodium hydrogen sulfite. Now here we can see that the equilibrium exists. Equilibrium is existing in each step. Each step equilibrium is existing. Okay. So now here again, sodium hydrogen sulfite, it's forming an addition product. How? The Na is getting added, so it is actually HSO3 minus which attacks the carbonyl carbon, forming O minus which holds the sodium. So O minus is holding the sodium. You are left with HSO3 minus, which can be written as OSO2H minus. So that's why the linkage is this, OSO2H. Okay, so proton transfer, minus H plus and plus H plus. So what is happening? Sodium and H, they are actually exchanging. So rather than transfer, I will say it is exchange of H plus taking place with Na plus. Okay, so then you are getting, in place of Na plus, H is coming and you are getting OH. So this is the bisulfite addition product, which is forming a white precipitate which is crystalline in nature. And so this can be used as a test for carbonyl as well. Now please remember, this is useful for the separation and purification of aldehyde. Why? Because you can convert it back to the original carbonyl compound by treating it with dilute mineral acid or alkali. So you treat it with dilute HCl or NaOH, you will get back the original carbonyl compound. So I hope the explanation is clear. Addition of Grignard. For this, I will say that when I take HCHO, the addition of Grignard takes place in this manner, that Grignard is RMGX. So RMGX has a speciality. And what is the speciality? Above Mg, it is positive. Above carbon or alkyl group, it is negative. Oxygen is a delta negative. Carbon is a delta positive. Now, this R, which is a delta negative, acts as a nucleophilic end, attacks the carbonyl carbon, electrophilic site, and oxygen opens up. So you get HCO minus that holds MgX. O minus holding MgX. 1H was already there and R has attacked. So this is your addition product, which is known as adduct. And this is susceptible to hydrolysis by HOH, that is water. And when it hydrolyzes, this bond breaks. Oxygen to magnesium bond breaks. Oxygen can hold H, Mg can hold OH. And you can get RCH2OH, which we can see is a 1 degree alcohol. Okay, plus a side product which is MgOHX. So when you use formaldehyde, you get 1 degree alcohol. When you use any other aldehyde like this, then what will happen? Let me show with R-MgX. Same thing I will always say. Keep in mind delta positive, delta negative, here delta negative, here delta positive, and then only you will be clear with the concept. Let this attack here, let O minus open up and hold MgX. So the addition product will be RCO minus opening up, holding MgX, H was there and R dash has attacked, and this is your intermediate or the addition product, which is susceptible to hydrolysis, HOH, and the bond between oxygen and magnesium is having greater electronegativity difference, and this breaks up in this manner, and the products are what? RCH, R dash, OH, and MgOHX. So we can see that this carbon is having 2 alkyl group. It's a 2 degree. So 2 degree alcohol is obtained from RCHO. Likewise, from ketone, you will get a 3 degree. Okay. So from ketone again, you will get a 3 degree alcohol. By same method, R dash attacking, oxygen opening up. So you have RC, oxygen holding MgX. There was an R, there is another R dash. This is the addition product, susceptible to hydrolysis, HNOH. This bond breaks, HNOH attaches. So you get RC, here there is R, again R dash, 1 OH, for which this carbon is a 3-degree carbon and giving 3-degree alcohol with the side product MgOHX. So this is the summation with Grignard reagent. If I use formaldehyde, I get 1-degree alcohol. If I use any other aliphatic aldehyde other than formaldehyde, I will get 2-degree alcohol. And if I use a ketone, I will get 3-degree alcohol. Next. Moving on to the next. Addition of alcohol. Okay. Alcohols also get added up. So let me see. R C double bonded OH. Okay. So what is happening? Addition of alcohol in one equivalent amount, 1 mole of alcohol, will give me hemiacetal, which is alkoxy alcohol. Why? Because the same carbon is having alkoxy as well as alcoholic OH group. How we are getting this O minus is holding this OR dash minus and it's attacking here. So you got, there was R, CH, O opened up to hold R dash, okay? And then you got what? You got OH. How? See, dry HCl gas is used over here. Why you know? Because in order to increase the electrophilicity over the carbonyl. When you use dry HCl, the oxygen gets protonated in presence of H+. Oxygen has lone pair. So the lone pair will abstract the proton and it will form OH+. The moment it forms OH+, it is more electrophilic in nature and it is more prone to nucleophilic attack. Keep in mind that this neutral alcohol also acts as a nucleophile. It can attack with its lone pair. Okay. However, the mechanism goes on stepwise. It gives you first hemiacetal, that is alkoxy alcohol, and then with another mole of R-OH, presence of H+, gives you acetal, that is geminal dialkoxy compound. Geminal means to the same carbon, two alkoxy groups, dialkoxy, are attached. This is the concept which I told you just now, that is dry HCl protonates the oxygen of the carbonyl. So when it protonates the oxygen of the carbonyl, what happens? This is a double bonded O, and if the lone pair holds the H+, then there is a positive charge over here and there is one lone pair remaining. So another over here. See, this was oxygen 1, 2, 3, 4, 5, 6. So these two electrons, okay. So one lone pair will hold this thing. Just a minute. This is the oxygen atom with one lone pair. The proton is abstracted and oxygen gets a positive charge. Since it gets a positive charge, it is more prone to a nucleophilic attack. The nucleophile will attack here and this oxygen will open up in order to become neutral. So to increase the nucleophilicity over the carbonyl carbon, dry HCl gas is used. If I use a ketone, I will not get acetal, but I will get a ketal. So this is obtained using ethylene glycol. It is CH2OH and another CH2OH, where we can see that there is this type of reaction taking place. Okay. So it's almost elimination of H2O with ethylene glycol. See, it is ketone R, C, double bonded O and R. And what is your ethylene glycol? Ethylene glycol is CH2OH and CH2OH. This is ethylene glycol. Remember in this manner that H2O gets eliminated. So when you remove or you scoop out this H2O, when you remove this, what you will get is, the one which you will get is, see, R, C, R. Double bond was there, so this is the bond. It is bonded to oxygen, this oxygen, and a CH2 and a CH2, which is bonded to this oxygen. And this is your cyclic compound that you have got, that you can see in this ethylene glycol ketal by the elimination of H2O. Next, moving on to addition of ammonia and its derivatives. Ammonia is a nucleophile. Why? Because it has a lone pair above. This ammonia can be written as NH2H. Nitrogen has a lone pair. Now, when I substitute this H by anything else, it becomes derivative of ammonia, right? So, what happens is, this lone pair above nitrogen, okay, this acts as a, it makes it acts as a, to act as a nucleophile, and it will attack the carbonyl carbon. Oxygen will open up. Okay, so when oxygen opens up, it abstracts this hydrogen. So we can see NH2 attacks this carbonyl carbon, and there is NHZ, an oxygen holding proton. Now what happens is minus H plus and plus H plus, proton exchange. See, this nitrogen has lone pair. It comes and forms a multiple bond. So there is a multiple bond between carbon and nitrogen. And when this opens up, actually it holds this proton and it opens up. So I always say remember it as minus H plus plus H plus. From here this H plus is getting removed and OH minus is holding it, forming H2O. And what is happening? The lone pair comes and forms a double bond between carbon and nitrogen, and so you get this. Okay, so now if you have to write it directly, how will you write? So let us see that. Okay, so if I have to write like any carbonyl compound, RC double bonded OH, when I'm giving H it is aldehyde, and aldehydes are more reactive than ketones towards nucleophilic addition. So I am telling this is NH2 and this is Z. If it is ammonia, then Z is equal to H, and if it is derivative, then Z is something else. Now when I write directly the structure of the product, what I will do is I will just remove H2O and combine the two ends, carbon and nitrogen end, by a double bond, right? So let us see, R, C, H was there and a double bond. Because I have removed H2O, I will join it with nitrogen and Z remains. So there is elimination of H2O and there is a double bond formation between carbon and nitrogen. That is what is happening here. When this is Z, I am getting C double bonded NH, which is known as imine linkage. If Z is equal to R, that means it is NH2R. It's amine, and what we will get is substituted imine, as if in the H imine, in the structure of imine, the H is substituted by alkyl group. And this is known as Schiff's base. Keep this in mind. This part is important for the Viva part of your board practical exam. Okay. Next, hydroxylamine has a structure of NH2OH because Z is equal to OH. Hydroxylamine forms oxime. How it forms oxime? By the reaction of C double bonded O with hydroxylamine, there is elimination of H2O and there is combination of carbon to nitrogen by a double bond. That is what is seen here. It's known as oxime linkage. C double bonded NOH is known as oxime linkage. So hydroxylamine gives oxime. Hydrazine. What is hydrazine? Hydrazine is NH2NH2. Why NH2NH2? Because this is Z. Z is equal to NH2. So again I will say C double bonded O. This loses H2O and it joins in this manner which is known as hydrazone. Hydrazine will give hydrazone. Phenylhydrazine. So what is the structure of phenylhydrazine? Remember that hydrazine is NH2NH2. Now when you substitute 1H of hydrazine by a phenyl ring, what you get is phenylhydrazine. So NH2, NH and this is your phenyl ring. So this is phenylhydrazine and this is your Z part. And there is elimination of I'll say H2O when it reacts with carbonyl. How? This H2 and this oxygen gets eliminated and the product is having C double bonded N linkage with rest of the part as it is, and from phenylhydrazine you will obtain phenylhydrazone. Next is 2,4 DNP. When you do the chemistry practical for class 12, you will see this structure 2,4 DNP and the full form is 2,4 dinitrophenylhydrazine. Most of the students end up in saying 2,4 dinitrophenol. Please don't say phenol here. It's phenylhydrazine. Now how to derive the structure of 2,4 DNP, dinitrophenylhydrazine? So the structure begins with hydrazine. NH2, NH2 is hydrazine. What is phenylhydrazine? That means I substitute 1H by the phenyl ring and I will write NH and NH2. This is phenylhydrazine. Now 2,4 dinitrophenylhydrazine. That means this is phenylhydrazine. This is carbon number 1. 2 position there is a nitro and 4 position there is a nitro, and this is the structure of 2,4 dinitrophenylhydrazine, 2,4-DNP. When it reacts with a carbonyl carbon C double bonded O, then there is elimination of H2O and you will get 2,4 dinitrophenylhydrazone. The structure will be having this. So whatever is your carbonyl, remember the root of the reaction, then you will not make any mistake in drawing the complete structure of the product. So this is N, join it by a double bonded C, and this is it. So if it is acetone, this will be CH3CH3. If it is acetaldehyde, this will be CH3-1H. If it is formaldehyde, it will be both H. So please remember that this is the root of the reaction, how the reaction occurs by the elimination of H2O and by the combination of carbon to nitrogen. Next, moving on to semicarbazide. So what is the structure of semicarbazide? Semicarbazide has NH2, NH, C double bonded O, NH2 structure. This is your Z part. Now here the product obtained by the elimination of H2O is semicarbazone, and remember a question comes, which of the two NH2 is involved in the reaction? So there is A, this is A side NH2, this is B side NH2. Which one is acting as the nucleophilic end? This is also a nucleophile. This is nitrogen is the nucleophilic end. This nitrogen also is a nucleophilic end. So which nitrogen is acting as a better nucleophile? For that reason, please see the structure once more of semicarbazide. It has NH2, NH, C double bonded O, NH2. This is the structure of semicarbazide. Nitrogen has lone pair here. This nitrogen is also having lone pair here. So for that reason I said this is A end, this is B end. Both are nucleophilic end because they are having a lone pair. But this nitrogen with the lone pair is in delocalization with the carbonyl linkage. So for that reason, this nitrogen, the lone pair above nitrogen, goes into resonance and is less available for nucleophilic attack. So I will say the B end has less nucleophilicity. It has less nucleophilicity. Why? As the lone pair over nitrogen is involved in resonance. It is involved in resonance and so is less available to act as a nucleophile. So this is the answer to it. So if I say out of A and B, which is acting as a better nucleophilic end and which is getting involved in the elimination of H2O, answer is A site. Let us see how. This is C double bonded O, carbonyl, and you have NH2, NH, C double bonded O, NH2. This is the structure of semicarbazide, right? So semicarbazide has this type of structure where we can see there is elimination of H2O and there is combination of the two. So what we get? The addition product by the elimination of H2O, C double bonded N, NH and C double bonded O, NH2. So this end is getting involved in the reaction and acting as the nucleophilic end. Next, after this we go to the reaction which is reduction. We have already seen that aldehydes and ketones reduce to alcohol. Aldehydes like RCHO undergo reduction to form 1 degree alcohol. Ketones undergo, so for ketones I will say RCOR. This undergo reduction to give 2 degree alcohol. Okay, secondary alcohol. It can give this by catalytic hydrogenation or by strong reducing agents like NaBH4, sodium borohydride, or LiAlH4, lithium aluminium hydride. Next, reduction to hydrocarbon involves two name reaction. One is Clemmensen and the other is Wolff-Kishner reduction. In Clemmensen reduction, it is involving ZnHg, zinc amalgam, and dilute HCl. This is dilute HCl and it is forming hydrocarbon. Just remember, in this double bonded O system, H2 will be coming. And there is elimination of H2O. You get H2O as the side product here. So this is Clemmensen reduction. You have to remember this is another name reaction. Next you have what? Reaction with ethylene glycol. It's a reduction again, ethylene glycol, and that too, first you treat it with hydrazine and just like the previous case, there is elimination of H2O. First there is elimination of H2O. Okay, so there is elimination of H2O. Let us see this properly. This is getting eliminated, this H2O, and you get C double bonded N NH2 by the elimination of H2O. And with ethylene glycol, remember again like the previous case, C double bonded system is changed to CH2, and which I have highlighted in blue, that is in N2 is getting eliminated. N2 is the side product. Here H2O is the side product. So these are the two methods of reduction to hydrocarbon and these are the two name reaction. Moving on to oxidation of carbonyl. Aldehydes are more effectively oxidized. Ketones are not readily oxidized with difficulty under drastic or elevated temperatures and conditions, vigorous conditions. So aldehydes are oxidized by common oxidizing agents like nitric acid, KMNO4, K2Cr2O7, etc. And even mild oxidizing agents like Tollens reagent and Fehling solution. Now this in your chemistry lab, you might have seen that when you are detecting a carbonyl linkage, aldehydes, be it aldehydes, carbonyl can be aldehydes and it can be ketones also. Aldehydes and ketones collectively give the 2,4 DNP test, and in this 2,4 DNP test, they will give you an orange red PPT, orangish red or reddish orange PPT you will get. But then how will you know whether you have an aldehyde or ketone? Remember that aldehyde responds to Tollens test, Tollens reagent test, and it gives a silver mirror with Tollens reagent test due to the formation of Ag as precipitate. And aldehyde also gives Fehling solution test or Fehling solution test, and it gives a red PPT. Remember that this is not for aromatic aldehydes. That means aromatic aldehydes will not respond to Fehling's test. Only aliphatic aldehyde responds to Fehling's test. Tollens is for aliphatic as well as aromatic. What will you do? What is Tollens reagent? Now, Tollens reagent is ammoniacal silver nitrate solution. It is ammoniacal silver nitrate solution. Now, silver nitrate solution is actually prepared in ammoniacal or alkaline, a basic medium. So when you add to the sample of aldehyde this Tollens reagent and you heat it in a water bath for some time, what you get is a silver mirror. What you get is a silver mirror due to the formation of a precipitate of silver. Okay. Now remember one more thing, that Tollens reagent and Fehling solution, these all are mild oxidizing agents. They are mild oxidizing agents, and for that reason ketone does not respond to Tollen and Fehling. Ketone will not respond to Tollen and Fehling because Tollen and Fehlings are mild oxidizing agent. Now after Tollen's reagent, the question arises, how are we supposed to prepare Fehling solution? Fehlings is a mixture of Fehling A plus Fehling B in equal volumes in 1:1 ratio by volume. Fehling A is aqueous solution of copper sulfate and Fehling B is known as Rochel's salt. It is known as Rochel's salt, which is sodium potassium tartarate. And when you mix them in equal volume and you add it to the sample, that means to the sample you're adding Fehling solution and again you are heating it in water bath for some time, then you will get a brown red PPT. You will get a brown red PPT of Cu2O. And this is not obtained from aromatic aldehydes. Keep in mind. Then how are we going to test ketone if we are not giving? So if ketone is not giving, it is not giving Tollens and it is not giving Fehling's test, then what does it give? DNP cannot be the confirmatory test for ketone because 2,4-DNP test is given by aldehydes as well. So for ketone, there is a test which is known as sodium nitroprusside test. This is a reagent which is used to confirm the presence of ketone. How? You will take the sample that contains ketone and you will add NaOH to it and then add sodium nitroprusside to it. When you add sodium nitroprusside to it, the only thing is you need to mix it very well. And after you mix it well, you will get a solution which is red in color. So you obtain red coloration and understand the difference between coloration and PPT. PPT means it is insoluble and it separates in the solution. But coloration means the entire solution looks like red colored solution. So for your practical viva, you need to know all the chemical reactions, all the formula of all the reagents. Coming back to our topic. So let us see. This is what I have already said. Mild oxidizing agents like toluene and phenyl, it can oxidize aldehyde. But oxidize to what? Oxidizes it to carboxylic acid, obviously. So CHO gets oxidized to carboxylic acid. This is an example of ketone. I am coming to it later on. See over here, again aldehyde reacts with toluene. 3OH minus is for ammoniacal medium and you get a precipitate of silver, which is the silver mirror. And the sodium salt, I'll not say sodium salt exactly, the salt is obtained as RCOO minus. Okay, so this is the side product, which is the carboxylate anion. Next is Felling's test, where I told you it is two solutions, Felling A, Felling B, in equal volumes you mix up. I told you what is Felling A, what is Felling B, same thing here. And what you will obtain is a reddish brown PPT of Cu2O. Okay, so this is it. Now coming to the ketone part, there is a rule which is known as Propoff's rule that will tell you which set of compound is your major product for ketones. Okay, so for ketones, which set of compound is your major product? Like you have taken this type of ketone, both the side of the carbonyl are different. When you oxidize it, remember that the bond can break between C1 and C2 and between C2 and C3. If it breaks between C1 and C2, remember that the last carbon will get converted to COOH. So carbon number 1 and carbon number 2 gets converted to COOH. Your product will be this two. Between C1 and C2 will be this two. See this RCOOH, because last carbon gets converted to COOH, I said. And the next one, this carbon gets converted to COOH. So you get R dash CH2 COOH. Next, if it is breaking between C2 and C3, then this carbon will get converted to COOH, carbon number 2. So you get what? You get RCH2COOH. And it is this carbon number 2 that has got converted to COOH. And in the other part, you will get what? R dash CH2. So this CH2 is this COOH and you get R dash COOH. Now, always remember, Propoff's rule says what? The smaller alkyl group, smaller R, remaining with C double bonded O will give you the major product, Now, if I assume that R dash is having a greater bulk factor than R, or R dash is having more number of carbon atoms than R, then this becomes more bulky. and this becomes less bulky. So my way of bond breaking where C2C3 is breaking and the R, which is less bulky, is remaining with C double bonded O while C2C3 is breaking, this will be my major product set. Suppose I give you an example. Okay, I need to go to the extreme right side for the example now. Suppose I say CH3, C double bonded O, CH2, CH3. This is an example and I am doing oxidation of it. And as per this, what will I say? This is my way of breaking. Say this is 1 and this is 2. So when I get it into two ways, I say this is one way of breaking, this is two way of breaking. For one way of breaking, the last carbon gets converted to COOH. So I get HCOOH. Along with this will get converted. So I will get CH3, CH2, COOH. This is one set. And for carbon number 2, again this carbon will get converted. So I get CH3, COOH plus this carbon gets converted. So CH3, COOH. So 2 moles of the same product I am getting for this. Now which set is the major product? My less bulky group is CH3. So where, just a minute. So where this is happening, no. My less bulky group is CH3. So where this CH3 is remaining with C double bonded O like this, that will be my major set of product. See, if it breaks in one manner, then CH3 is not remaining with C double bonded O, right? Can you realize that? So this way of bond breaking will give me my major product. That is as per the rule which is known as Propoff's rule. Okay, so I think the concept is quite clear now. Moving on to the next part. Yes. So after this comes oxidation of methyl ketone. This is a name reaction again which is known as haloform reaction. Okay, in haloform reaction, it is a reaction for a particular type of carbonyl compounds that contain a ketomethyl group. That means C double bonded OCH3. It is known as ketomethyl or methyl keto. Anything is allowed. This group, this type of linkage, C double bonded OCH3, when it reacts with NaOX, which is known as sodium hypohalite, it is an oxidation method, and this NaOX is prepared in situ in the reaction mixture by the reaction of X2 and NaOH. Okay, this gives you NaOX. Okay, so this is known as sodium hypohalite, and if I use I2, then it is NaOI. If I use Br2, it is NaOBr. Now remember that this test is not only a test for carbonyl, it is also a test for alcohols that contain CH3 CHOH linkage, and that can get oxidized to a ketomethyl group by the removal of this 2H. Oxidation is removal of H2. So this type of alcohol containing CH3 CHOH group by the removal of H2 by oxidation lands up to the formation of a ketomethyl compound only. So these types of alcohols containing what? CH3 CHOH linkage, CH3 CHOH linkage will be giving you this test. Okay, so this test is a test for distinguishing compounds containing ketomethyl and not containing ketomethyl, for alcohols containing CH3 CHOH linkage and not containing CH3 CHOH linkage. But keep in mind that that is a test which is known as iodoform test. If I use NaOH and I2 forming in situ NaOI, then in place of CHX3 or CHCl3, I will get CHI3, which is a yellow precipitate. It's a yellow precipitate, and so it can be used as a distinguishing test. So how can you distinguish formaldehyde and acetaldehyde? Acetaldehyde response gives yellow precipitate with I2 and NaOH. Response to iodoform test. How can you distinguish methanol and ethanol? Ethanol will respond to iodoform test, but methanol will not. Okay, acetone responds to iodoform test. So these all things, okay, or now over here, please keep in mind one thing, that when you are using any test as a distinguishing test, there should be some observable change. Maybe some precipitate you are getting, maybe some smell you are getting, characteristic smell, or maybe some fumes, some gas is getting evolved which you can test it out, some color change you are getting. So any observable change, any distinguishable change can be used as a distinguishing test. Next, moving on to the example 8.4. It's very important. An organic compound A having a molecular formula C8H8O forms a red precipitate with 2,4 DNP. So I can say it is responding to 2,4 DNP test. That means it can be a carbonyl compound, an aldehyde, or a ketone. As per this information, it gives yellow precipitate. It gives yellow precipitate on heating with I2 in presence of NaOH. That is what I said just now. So it gives iodoform test. So obviously it is containing a ketomethyl group. Again, it can be an aldehyde or a ketone, but obviously it contains a ketomethyl group. Next, it neither reduces, a cross over here, for Tollens reagent or Felling's solution. So it's a cross here. So obviously it is not an aldehyde, and so it is a ketone. So it is not an aldehyde, but it is a ketone. So we'll say it from here that it is a ketone. Okay, after this, one more thing I'll say. If it is a ketone, this ketone should obviously contain this linkage. COCH3 linkage is present in the ketone. Okay, now next is, nor does it decolorize bromine water or Bayer's reagent. So here again I will say, when I give Bayer's reagent is KMNO4. So when I give KMNO4 or I give bromine water, there is no reaction. So it is not an alkene also. No unsaturation is present. Not an alkene. No C double bonded C system is present rather. Okay, so on drastic oxidation, it gives you, so I will say strong oxidation, it gives C7H6O2. Now you identify. First and foremost, I'll tell you the molecular formula is C8H8O. When you remove C double bonded OCH3 from here, you are removing 2 carbon. So you are left with C8 से 2 carbon अगर जाता है तो ये होगा C6. Now H3 is over here. So 8 minus 3, यहाँ से 8 था. C6, H5. Okay, oxygen is getting removed. So it is C6H5. COCH3. So acetophenone is the compound. Now From this, you have to give all relevant equations with this compound acetophenone. This is your 2,4 DNP structure. Remove H2O, this oxygen, and remove this 2H and join this carbon to this nitrogen with a double bond, C, and you get the product. Next, it is telling that A reacts, it undergoes oxidation to give you C7H6O2. So it's the acid over here. And this undergoes iodoform test, so COO minus. You have used NaOH, so COO, Na. If you use KOH, it will be COOK, and with this CHI3, one carbon atom from this CH3 actually gets removed due to the formation of CHI3. Okay, so this is the reaction, and it is very, very important reaction for your board exam. Next, reaction due to alpha hydrogen. Remember, this alpha hydrogen of carbonyls are acidic hydrogen due to the polar nature of this bond. This bond is a polar bond for which this any hydrogen attached over here behaves as acidic hydrogen. Okay, any hydrogen attached to, it's just a minute, any hydrogen attached to the carbon which is attached to C double bonded O. Why? Because C double bonded O is the carbonyl linkage and it's a functional group. So anything attached to the functional group is the alpha carbon. And the alpha hydrogen is acidic hydrogen. This hydrogen is the acidic hydrogen, and this hydrogen can be abstracted by any base which is there in the medium. Remember that with a dilute base, what happens is it abstracts this H and the negative charge is obtained over the carbon. See, the base abstracts proton and the negative charge is obtained over this carbon, and this intermediate is resonance stabilized intermediate. So the alpha hydrogen getting removed means this is your conjugate base, and the conjugate base is resonance stabilized. Such a reaction is seen in aldol condensation. Aldol condensation reaction takes place with carbonyl compound containing at least one alpha hydrogen in presence of dilute alkali as catalyst. Why? Because this can be written as CH2H. If there is a base in the medium, it will abstract this proton and it will give you a negative charge over here. That means you will get a CH2 minus CHO attached over here. This acts as a nucleophile to another carbonyl linkage. It acts as a nucleophile. So what happens? This negative charge will attack here and this opens up as O minus. So what you have obtained is, see, a CHO was here, so this is the CHO. CH2 was here, this is the CH2. It has attacked to this carbon, so this is this carbon. Oxygen has opened up and O minus in the medium is H, so OH. And there was this hydrogen, it is this. There was this methyl, it is this. So you get a compound where it contains aldehyde functional group and alcohol functional group together. So it is known as aldol. That means aldehyde and alcohol functional group is present in the same compound. And what is the IUPAC name? 1, 2, 3 and 4. 3 position there is hydroxy. So 3-hydroxybutanal. And it is, when you heat it, it loses H2O and the H2O is removed from alpha and beta. See, this carbon is alpha carbon because it has the functional group CHO. It is directly attached to the functional group. So this is your alpha carbon. Next to it is beta carbon. So there is alpha beta elimination. Alpha carbon से H जाएगा, beta carbon से OH जाएगा, और alpha और beta के बीच में there will be a double bond. So this is known as alpha beta unsaturated carbonyl compound. So you see there is a CHO group attached over here and it is having alpha beta unsaturation, and this is your condensation product. So if your question is not aldol condensation, do not give heat to remove H2O. If the question is draw the structure of the aldol, please stop till this. If the question is draw the structure of the aldol condensation product, then it is required to heat and remove H2O. Next, this is the example with ketone. Same thing happens over here. You obtain a ketol, that is a C double bonded O and OH attached to the same compound. This is your alpha, this is your beta. There is elimination of H from alpha and OH from beta, and there is a double bond between alpha beta, and it is aldol condensation product. Rather, I'll say it is a ketol condensation product. Okay. Next, moving on to cross aldol condensation. Cross aldol is a reaction between two different aldehyde. This is also having alpha hydrogen, this is also having alpha hydrogen. So if both are having alpha hydrogen, you will get 4 set of compounds. One thing let me tell you, if anyone is asking you to draw the structure of the aldol condensation product, then you have a technique. Suppose I say CH3CHO, aldol condensation product इसका draw करना है. So 2 moles of the aldehyde reacts, तो इसको ना ऐसे लिखोगे. You write CH3CH double bonded O. Open up the structure and write it in this manner and project दूसरे मोल का alpha hydrogen to alpha hydrogen and write it in this manner CH3CHO, and then you are given dilute OH minus number 1 and number 2 heat because you want to write the structure of the condensation product. Remove H2O and join these two ends by a double bond, and you will get CH3CH double bond CHCHO. See, this is your aldol condensation product. Next example. Now next example in cross aldol, if anyone is telling you to draw the structures of the products, say cross aldol, 2 different are there. Okay, so let me say one is CH3CHO and the other is CH3C double bonded O CH3. So first is you will get 2 moles of this aldehyde will give you this compound. Same thing which I have shown you just now. CH3CH double bonded CH CHO. 2 moles of this will give you another compound. How? Say you write it CH3CCH3. Project the double bonded O. Remove H2 from another mole and you are left with 1H because there is CH3. So 1H and rest of the structure C double bonded O CH3. That is, removal of H2O from 2 moles of this compound will give you this. So you got 1 pair. The next pair can be by removal of. The next pair can be by removal of, say, oxygen from this and alpha hydrogen from this. So I will write CH3CH double bond, oxygen is removed and remove 2H from here. You will get CH, C double bonded O, CH3. This is one product. Another product is opposite you do. Remove oxygen from here and remove 2 alpha hydrogen from here. And you will get what? You will get, I'm drawing this structure first. So you will get CH3, C, CH3. I have removed oxygen. So double bond. And I will combine with this. So CH and a CHO. So please see, I have got 4 compounds, 4 set of products, okay, in cross aldol. Now over here, this example you can see, this is having no alpha H. So I cannot remove H2 from here. So this product is obtained by removal of oxygen from here and removal of 2H from here. You have got this as the major product. Other reactions are Cannizzaro reaction, which is a special reaction with a compound that does not contain alpha hydrogen. It undergoes disproportionation reaction, that means self-oxidation and self-reduction. The compound is undergoing oxidation to form the acid and reduction to form the alcohol in presence of concentrated alkali and heat. So this alcohol is your reduction product, the acid is your oxidation product. This is the other reaction. Now the last reaction is electrophilic substitution reaction, and it is aromatic electrophilic substitution reaction. See, this linkage is what type of linkage? This is a C double bonded OH linkage. Now here we can see that this is having minus R effect. So for minus R effect, it is actually CHO group is deactivating. And why it is deactivating? Because it has minus R effect, because it reduces electron density over the benzene ring, due to minus R effect. So it is deactivating and hence it is meta orienting. Why? Because when the electron density moves out, then what happens? There is a positive charge developing over the ortho-para positions. So this meta position has relatively greater electron density, and an electrophile over here is NO2 plus. It will obviously attack the meta position. So it is meta-nitrobenzaldehyde as the product. So it is meta-orienting, meta-directing because it is deactivating CHO group. So this is the in-text question. Arrange the following compound in increasing order of their nucleophilic addition reaction. Ethanal, aldehyde, propanal, aldehyde with one more carbon atom, propanol ketone, butanol ketone. So I will write this as 1, 2, 3 and 4. Aldehydes are more reactive. 1 and 2 is more reactive, but ethanol is having less number of carbon atom. So I will say 1 is most reactive, then comes 2. Now, butanol and propanol, dono kya hai? Ketone, so less reactive. But propanol is more reactive because it has less number of carbon atoms than butanol. So it is 4, 3, 2, 1. So next is toluyldehyde. Toluyldehyde contains a CH3 group and aldehyde, nitrobenzaldehyde, nitro group and aldehyde, and acetophenone is a ketone. Benzaldehyde is as such less reactive. Toluyldehyde increases the electron density, okay, over the ring and over the carbonyl carbon. So if I say this is 1, this is 2, this is 3 and this is 4. So aldehydes will have greater reactivity. Nitrobenzaldehyde, due to the electron withdrawing group nitro, it will increase the delta positive character over the carbonyl carbon. So this is more reactive. Okay, this is more reactive. And then I will say is benzaldehyde. And then I will say para-toluyldehyde because it is electron donating group. It is again pushing electron to delta carbonyl carbon and reduces its delta positive character. Okay, I want it to be increased. So that is minimum. Okay, and now comes ketone. So then is 4. 4, 2, 1, 3. Achha, if you think that it is something else, do drop it in the comment section and let us discuss about it. Next, predict the products. Here it is hydroxylamine NH2OH. Remove NH2O and join the two ends. This end and this end with a double bond. Rest remaining the same. Next is 2,4-DNP. Remove oxygen and remove the 2 hydrogen. Let me draw it in a different manner. Remove oxygen and remove the 2 hydrogen like this and join this carbon to this nitrogen with a double bond. Next I can see semicarbazide over here, which is the nucleophilic end. This. So this H2 and this oxygen will be removed and you have to join this carbon and this nitrogen with a double bond, rest remaining same. So R, CH, double bond, CH, I said CH, double bond, and oxygen is removed. Okay, so oxygen is removed and joined with the next nitrogen and it has NH and it has C double bonded O and it has NH2. So this is the complete structure of the product. Next one, again, you remove H2 from here, it's amine, remove oxygen and you remove H2 in this manner, okay, in this manner. Join this carbon to this nitrogen and you will get the product like this. So this is the ring, this is CH3, double bonded O, remove the oxygen, join it to the nitrogen, remove H2, join it to the CH2 and CH3. This is the major product. So today's elaborate discussion is till this, and I think I could plunge in to the basic concepts of the chapter of chemical reactions of aldehydes and ketones. Please explore. The more you explore, the more you learn, and learning is a continuous process. So, bye all of you. Thank you all of you for being with me in this session. Hoping to meet you soon in the next session. Till then, bye.